Example 1, evaluate the integral of the square root of 9 minus x squared over x squared dx. Let x equal 3 sine theta, where negative pi over 2 is less than or equal to theta, and theta is less than or equal to pi over 2. Then dx equals 3 cosine theta d theta, and the square root of 9 minus x squared equals the square root of 9 minus 9 sine squared theta equals the square root of 9 cosine squared theta equals 3. The absolute value of cosine theta equals 3 cosine theta. Note that cosine theta is greater than or equal to 0 because negative pi over 2 is less than or equal to theta, and theta is less than or equal to pi over 2. Thus, the inverse substitution rule gives the integral of the square root of 9 minus x squared over x squared dx equals the integral of 3 cosine theta over 9 sine squared theta times 3 cosine theta d theta equals the integral of cosine squared theta over sine squared theta d theta equals the integral of cotangent squared theta d theta equals the integral of open cosecant squared theta minus 1 close d theta equals negative cotangent theta minus theta plus big C. Since this is an indefinite integral, we must return to the original variable x. This can be done either by using trigonometric identities to express cotangent theta in terms of sine theta equals x over 3, or by drawing a diagram, as in figure 1, where theta is interpreted as an angle of a right triangle. Since sine theta equals x over 3, we label the opposite side and the hypotenuse as having lengths x and 3. Then the Pythagorean theorem gives the length of the adjacent side as the square root of 9 over square root of 9 minus x squared, so we can simply read the value of cotangent theta from the figure. Cotangent theta equals the square root of 9 minus x squared over x. Although theta is greater than 0 in the diagram, this expression for cotangent theta is valid even when theta is less than 0. Since sine theta equals x over 3, we have theta equals the inverse sine of x over 3, and so the integral of the square root of 9 minus x squared over x squared dx equals negative square root of 9 minus x squared over x minus the inverse sine of x over 3 plus big C. Figure 1, sine theta, which is opposite over hypotenuse, is x over 3. Example 2. Find the area enclosed by the ellipse x squared over a squared plus y squared over b squared equals 1. Sidebar, figure 2, x squared over a squared plus y squared over b squared equals 1. In the graph, there's a y-axis and an x-axis and a point A0 and a point 0B. Back to the text. Solution. Solving the equation of the ellipse for y, we get y squared over b squared equals 1 minus a squared over, restarting that line, y squared over b squared equals 1 minus x squared over a squared equals a squared minus x squared over a squared, or y equals plus or minus b over a times the square root of a squared minus x squared. Because the ellipse is symmetrical with respect to both axes, the total area of big A is 4 times the area in the first quadrant, see figure 2. The part of the ellipse in front, in the part of the ellipse in the first quadrant is given by the function y equals b over a times the square root of a squared minus x squared. And x is greater than or equal to 0, but less than or equal to a. And so 1/4 big A equals the integral from 0 to a of b over a times the square root of a squared minus x squared dx. To evaluate this integral, we substitute x equals a sine theta. Then dx equals a cosine theta d theta. To change the limits of integration, we note that when x equals 0, sine theta equals 0. So theta equals 0. When x equals a, sine theta equals 1. So theta equals pi over 2. Also, the square root of a squared minus x squared equals the square root of a squared minus a squared sine squared theta equals square root of a squared cosine squared theta equals a times the absolute value of cosine theta equals a cosine theta, since theta is greater than or equal to 0 and theta is less than or equal to pi over 2. Therefore, big A equals 4 times b over a times the integral from 0 to a of the square root of a squared minus x squared dx equals 4 times b over a times the integral from 0 to pi over 2 times a cosine theta times a cosine theta d theta equals 4ab times the integral from 0 to pi over 2 time of cosine, restarting this line, 4ab, the integral from 0 to pi over 2 cosine squared theta d theta equals 4ab, the integral from 0 to pi over 2 1/2 open 1 plus cosine 2 theta close d theta equals 2ab open bracket theta plus 1/2 sine 2 theta, close bracket, on the interval from 0 to pi over 2, equals 2ab, open, pi over 2 plus 0 minus 0, close, equals pi ab. We have shown that the area of an ellipse with semi-axes A and B is pi AB. In particular, taking A equals B equals R, we have proved the famous formula that the area of a circle with the radius R is pi R squared. Note, since the integral in example 2 was a definite integral, we changed the limits of integration and did not have to convert back to the original variable x.